Today's lesson is on linear programming. Linear programming is a process, a method for solving some problems that can seem pretty complex. And it's a method of breaking them down into components that are easier to solve one by one rather than trying to solve the whole thing together. So that is what linear programming is. A method, and it's specifically a method for finding the minimum or maximum value of a function. So it's going to be something like you're trying to find the the maximum profit or the minimum cost, things like that. When we deal with linear programming, we have some vocabulary that we use. One word that you need to understand is the constraints. And the constraints, another synonym for that would just be limitations. So the constraints are things like budget, time, or space. Also, the constraints can usually be stated as an inequality. So these are inequalities. Inequalities that we will read the problem and we will write the inequalities to match up with what the problem is talking about. We have a couple more vocabulary words. One is the feasible region, and the feasible region is the area of possible values. And so again, if you look at that phrase, that's what it means. Feasible means possible. Another word for region is area. So we are going to graph these constraints, and when we graph the constraints, we're going to find the feasible region, the area of possible values. That means what would actually work? What situation would make this would make this problem possible? And so that's what we're looking at. The objective function is what you're actually trying to maximize or minimize, like profit. What are you trying to actually obtain with this study or this method that you're doing? So that's the objective function. The objective function will come at the very end. Sometimes it's maybe the most obvious one to define, but we wait until the very end before we actually use it. Let's look at an example. So this is just an example that came out of the book. Gillian is planning a green roof that will cover up to 600 square feet. She will use two types of plants, blue lagoon sedum and raspberry red sedum. Each blue lagoon sedum will cover 1.2 square feet. Each raspberry red sedum will cover 2 square feet. Each plant costs $2.50, and she must spend less than $1,000. Okay. I think you can see from that situation, there's a lot going on here. If we tried to go through and underline or highlight things like that, that would be a good idea. But even so, there's still just a lot going on. So take a minute to read through it again and try to decide, what are your variables even going to be? Because again, there's a lot going on. And so we're going to think about, what would those variables be? Think about that for a second. Okay, I'm going to tell you that the variables are the two different kinds of plants. Now, how would you know that? We're going to get to that, how you would know that, because we have a lot going on here. We have the different plants, we have different square footage, we have different costs, we have a lot going on. And so let's just keep talking, and I'll come back to you to talk about how do I know which ones are the variables. Okay, the constraints. Remember, another synonym for constraints is limitations. Let's go back to that problem and look at what are some of the limitations that there are. And think about that. What are the limitations? Read through the problem. Okay, hopefully you can see that the constraints are the budget, the money, and the area, how much space she has. And so here's how I know what the variables are. A lot of times I save the variables for later, because if I can think of what are the constraints, and the constraints are the area and the budget, so I'm going to go back and do some of that highlighting that we were talking about. She has blue lagoon sedum and raspberry red sedum. She's got those two things going on. She has the square feet, and she also has the cost. Well, the ones that are the constraints, the limitations, those are the budget and the area. The ones that are left over that I haven't used yet, not the budget, not the area, that's the plants. So now that you know what the constraints are, can you come up with the inequalities that would match with those constraints? So read through here, look for the money. How much does each one cost? Come up with a standard form inequality. Read it through again, look at the square footage. How much square feet does each one use? And come up with an inequality for that. So for the budget, each plant costs $2.50. Does not matter which kind of plant. So it's $2.50 for a blue sedum, and it's $2.50 for a red sedum. I notice I left off my zero there. If you wanted to include it, you could. Of course, we don't need it, but that is $2.50. So $2.50 for the blue, $2.50 for the red, and she has to spend less than $1,000. Let's do the same thing for the area. Look in the problem, see how much area each kind of plant needs, and then come up with an inequality to represent that. So the area is the blue sedum, those are the X's of the blue. The blue requires 1.2 square feet, and the red, that's the Y, the red requires 2 square feet. And she only has 600 square feet to use, so it all has to be less than 600 square feet. Okay, so my variables are my blue sedum, the blue and the red sedum. The budget, I have outlined that. The area, I have outlined that. There's one more thing in the constraint, or two more things in the constraints that we need to talk about, and that is that we cannot have a negative number of plants, right? So we cannot have a negative blue plants, and we cannot have negative red plants. And so we want to make sure that X is greater than or equal to 0, and Y is greater than or equal to 0. And so now we're going to take some time to set up our graph. And you might not know right now, why am I counting by hundreds? So let's go ahead and talk about why I'm counting by hundreds. So again, you can take a second to set up your graph, pause the video if you need to, and then we'll talk about what do I need to count by? How high do I need to go? So for the budget, I'm going to make a T-chart and a table of values. And I'm going to plug in my zeros for my X and 0 for my Y and see what I come up with. Well, if I take 1,000 divided by 2.5, that's 400. And 1,000 divided by 2.5 again is also 400. So I need to count up to at least 400. I'm going to look at my other area constraint and set up a table of values for that one. So 600 divided by 1.2 and 600 divided by 2. So if I plug in a 0 for 1.2, excuse me, if I plug in a 0 for X, then I get 600 divided by 2, which is 300. And 600 divided by 1.2, I believe that is 500. Okay, so those are my tables of values. That's how I knew to count up to 500. So once I get my tables, then I can set up my graph. Let's go ahead and graph these. So the budget goes from 400 to 400. Now, hopefully you can see that that's a slope of 1. So you could use your, use your straight edge, or you could just count down one, left one, down one, left one, etc. And that's going to be our first inequality. And we do need to think about, should it be dotted or solid? It does have an equal to sign. Since it does have an equal to sign, it should be solid. And the shading is less than, so since it's less than, we are going to go down this way. Remember, these are constraints, so they're limitations, and that helps a little bit make sense of to why they're down here as well. Okay, the other inequality goes 300 on the y-axis down to 500 on the x-axis, and so that also is less than. So I'm going to put my points here at 300 and 500. It is less than, which means that it is in this area. I might even come back just to make it clear and erase this area here because it's not in that area. The only area it is this kind of, what is that? Almost a rhombus shape. It's not a rhombus though, but you see this odd looking shape down here. It does not include the sliver up here. It does not include this sliver over here. So that is our graph. Now the last thing that we haven't graphed is the x is greater than 0 and y is greater than or equal to 0. So that if we wanted to draw lines in there, that would probably be appropriate to go ahead and draw a line here and a line here. But again, our area that we need is this area in here. Now, just like we were doing before in our last lesson on finding vertices, we need to do that same thing here. We need to find these vertices here, 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 and here. Those are the vertices that define our feasible region. Now, just like before, some of them might be easy. Our lesson yesterday, some of those vertices are pretty easy to find. Some of them are not as easy. But looking at this, I know 1, 2, 3 of them for sure. I definitely have a vertex at 0, 0. And I definitely have one at 0, 300. And I definitely have one at 400, 0. And the question is, well, what is this one? If you look at it really closely, if you did a good job with your drawing, it seems like maybe it is 250, 150. Does yours look like it's about there? I'm going to put a question mark because I think that's what it is, but it's definitely worth investigating. Well, one way to check our answer, do you know how we would check our answer? We would plug those numbers in here and see if they work. So if we do that, if I take 2 times 150, that's 300. I'm going to change my color here. So this would be 300. And then 1.2 times 250, if I do that on the calculator, I think that is going to be 300, isn't it? So that's 300 plus 300. That does equal 600. Seems like it's probably going to work. Let's go ahead and test it up here. Okay, to plug it into the top equation, I'm going to need my calculator. But 250 times 2.5 is 625. And 2.5 times 150 is 375. And 625 plus 375 does equal 1,000. Okay, so in other words, I was able to eyeball it. I came up with the right guess, and the guess did work. But you want to make sure you check that. Don't just try to do that and think that you've got the right answer without checking it. Now, what if that hadn't been the right answer? What if it looked like 250, 150, and I plugged it in here and it didn't actually work? Well, then that's a big bummer because then I have to go back and actually solve it, like do probably linear combination on these, elimination on these, and figure it out from there. So, but as long as we can see it, if it works and we can see it, then let's just go ahead and take that, okay? So let's go ahead and write down that last vertex. That last vertex is actually 250 and 150. Okay, the reason we do this is we are about to talk about maximizing the function. And as it turns out, the maximum value is always one of the vertices. It's never just some random point in there. It's not going to be any of these random points. It's always one of the vertices. Because if you can think about it, it's almost like that's where the maximum is just like pushing out to the maximum, okay? Or if it's minimizing, obviously 0, 0 would be our minimum. So those points, those vertices become very important for us. So the next step is to think about what are we maximizing or what are we minimizing. So here's the problem. It's the same exact problem written before, but we want to think of what is she trying to maximize, what is she trying to minimize. So if we read through it again, it says how many of each type of plant should she plant to maximize CO2 absorption. So she's trying to maximize the CO2 absorption. She's trying to help the planet, basically. So how much should she do? Well, let's look at the CO2. The CO2, the blue sedum, takes 1.4 pounds of CO2 per year, and the red sedum absorbs 2.1 pounds of CO2 per year. So that's what we're going to maximize. That's going to be our maximizing function. So we're going to write that as a function. And what we need to do next is we need to take our vertices and plug them in and see which one comes out to be the maximum or minimum value. Now, I will warn you here that there are some people who think they can do this in their head and they don't want to show any work because they say, I just have my calculator, I did it in my head, what have you. Well, guess what? I want you to show your work regardless. So we're going to go ahead and show our work, even on the 0, 0. I mean, come on, 0, 0. How hard is that? But is that really hard to show your work for? No, it's not. So we're going to plug each one in and we're going to see what comes out. So I'm going to take this maximizing function and I'm going to take my vertex and I'm going to plug it in. Well, guess what? That comes out to 0 pounds, which we already knew, but because our teacher makes us show our work, we're going to show our work. Next one, I'm going to take 0, 300. So I have 1.4 times 0 plus 2.1 times 300. And again, I know you can do this on your calculator, but if you're trying to sell this to somebody, like say, hey, I want to go up on the roof and plant this garden, you have to actually show them that you've done the math to do it. Okay, so this is 0. This is going to be 630 pounds. A lot better than 0 pounds, obviously. And then we're going to pick our next one, which I'm going to pick 400, 0. And I'm going to plug that in, 2.1 times 0. That's kind of hard to read, but that's 2.1 times 0. And so 1.4 times 400, I believe, is 560. And then our last one is 250 and 100. So we're going to take, sorry, let me scratch that out. 1.4 times 250 plus 2.1 times 150. And we're going to work this out. And when I work this out, this comes out to be, on my calculator, I'm getting 665. Okay. So here's the deal. This is how we maximize the carbon dioxide absorption. And we need to find out which one of those vertices, because it's always a vertex that works. That's how the graph works. We're going to figure out which one of our vertices, when I plug it in, gives me the maximum CO2 absorption. And so I've worked them all out, and I've found out that this last one is the best one. And so I'm going to say that she should plant 250 of the X's. What were our X's? Our X's were the blue. 250 blue plants and 150 red plants to maximize the CO2 absorption at 665 pounds per year. Okay. Obviously, that is a huge process, right? I mean, that took a long time to go through that problem. And so when we work these in class, they're going to take a while. Also, part of our assessment, like a test this time, is going to be for you to make up one of these problems and hopefully have a fun time with a partner making up a problem like this and seeing what you can maximize or minimize. But a big thing in this is showing our work. There will be a question like this in the final, And the final I'm giving you points for, are you showing me all of your steps? So you have to define the variables, come up with your inequalities, your constraints, graph those constraints, come up with the vertices, plug them in, and find the maximum value or the minimum value, depending on the situation. Okay, the other example on the next page, this has been a long one, so we will just save that one and do that one together as practice in class tomorrow.